Hi, I'm Brooke Byer, and I'm a grad student at the University of Rochester's Institute of Optics.
Hi, I'm Zachary Smith. I'm also a graduate student at the Institute of Optics.
So today we're talking about light that's visible and not visible. So the human eye can see from about 400 to 700 nanometers, but that's not the end of the electromagnetic spectrum. There are certain animals that can see beyond that region, including bees and some beetles, and I'm sure numbers of other animals. But we have a webcam that is kind of like a non-human eye. It's also able to see beyond what the human eye can see. So I have a basic TV remote. It's actually a VCR remote, but it actually uses infrared light to communicate with the TV or VCR. So here you can see a signal that's coming from the remote. And I can also shine this into the webcam. And we can see the signal from using the webcam. But now this is just a very basic webcam, but we can turn this into a spectrometer by adding a diffraction grating over the entrance to the webcam. So now you'll see how there's some white light that gets diffracted a little bit. So we can shine a laser if you have a laser. This is 632 nanometers, and we can take an overhead transparency, just so we're not marking up our actual TV monitor, and mark where the center is, where you're shining the light, and then mark where the first order diffraction spot is, so the one that's closest to where you're shining it. You can mark that, and that's going to be an indicator of where 632 nanometers would be diffracted to. We can also shine a white light. I just have a white LED. And we can shine this. And this white light contains all of the colors that we normally see. So we can mark also where blue is and where red is. And we know blue is about 400 nanometers. So now we have 2 points that we can use to calibrate our spectrometer. So now we're ready to shine our infrared source. If we shine the remote into the webcam and we overlap the direct light, we can mark where the infrared goes. And since we know we've marked that blue is for 400 nanometers and then the red is for about 632 nanometers, we can use those numbers to estimate that the infrared wavelength of the remote is 1000 nanometers. We can shine this white light, which is made up of the different colors of the visible spectrum. And we can mark where we see it diffracted, where the blue is and where the red is, and we know what wavelengths those correspond to. The blue is 400 nanometers, and the red, which we had marked from the laser, still will correspond to 632 nanometers.